work analyzed CLIP models are three safety objectives beyond overall accuracy. They are visual factor level robustness, out-of-distribution detection, and predictive uncertainty. For visual factor level robustness, we analyze it from two perspectives, which are robustness against visual factors and texture shape bias. For robustness against visual factors, we introduce the concept of factor-level effective robustness. It measures models' ability to achieve higher accuracy on a specific visual factor than its overall accuracy on the whole ImageNet X. And for texture shape bias, it means the proportion of accurate predictions made based on the object texture of shapes. For out-of-distribution detection, this task targets at identifying test data that do not belong to any of classes modeled in training distribution. With the popularity of CLIP models, zero-shot OOD detection is proposed, where allows flexible definition of in-distribution classes without training the models. Predictive uncertainty aims to classify images with calibrated prediction probabilities so as to match the empirical frequency of correctness. After the introduction to three safety objectives, we are going to talk about models of interest. The first group is CLIP. We consider both zero-shot CLIP models and ImageNet fine-tuned CLIPs. They have different visual encoders, including slightly modified ResNet or vision transformer. There are two training sources and multiple sizes of training dataset. And for fine-tune, we include two fine-tune procedures. And we compare CLIP with three groups of models. They are standard neural networks and models trained by contrastive learning, and those who pre-trained on more data. Then we introduce the datasets and metrics used for each safety objective. We use ImageNet X to assess models' robustness against visual factors, and Q conflict stimuli, and stylize ImageNet for texture shape bias. For OOD detection, we use maximum concept matching for zero-shot CLIPs and a maximum softmax score for other models. The in-distribution dataset is ImageNet, while the OOD datasets are iNaturalist, SUN, Places, Texture, and ImageNet O, and the metrics are AUROC and false positive rate at 95. We examine model performance on uncertainty estimate before and after calibration. We use temperature scaling as the calibration method. We use ID test for in-distribution dataset, and OOD datasets are ImageNet variants. As for the metrics, we use estimated calibration error and negative log likelihood. For visual factor level robustness, we have mixed observations. Training distribution impacts model robustness. The distribution can make CLIP models more or less robust than other models. Zero-shot CLIPs are similarly robust as others for difficult background. On smaller or larger factor, zero-shot CLIP are more robust. For pose or partial view factor, zero-shot CLIPs are less robust. For texture shape bias, zero-shot CLIPs are generally more shape biased. And for out-of-distribution detection, when trained on same source, classification accuracy of CLIP models correlates with their OOD detection performance. In contrast to previous findings that CLIP models are better calibrated, we observe that they are not always better calibrated. We also see that for CLIP that are originally worse calibrated than other models, with the help of temperature scaling, they benefit more than others. This suggests zero-shot CLIP models are relatively easier to calibrate when evaluated by ECE. We further studied the impacts of test time prompt. We noticed that prompt set does not impact visual factor robustness. As for models with different prompt sets, they still lie on the same linear trend, but it influences the performance of classification, OOD detection, and uncertainty estimates. However, no prompt set is always superior to others. In summary, this paper studied the effectiveness of CLIP models in the context of robustness to visual factors, OOD detection, and the reliability of uncertainty estimation beyond overall classification accuracy. We have the following observations. CLIP models are generally more robust than ImageNet classifiers on 6 visual factors. The training distribution plays a key role. CLIP models are biased towards shape when making predictions. When trained on the same source, the classification accuracy of CLIP models correlates with their OOD detection performance. CLIP models are not always more calibrated than other ImageNet models, but they are relatively easier to calibrate across diverse distributions using temperature scaling. Both training data distribution and quantity impact CLIP's predictive uncertainty.